Hello everyone. Uh, Hope you're doing all well. Welcome to another video in which we'll be discussing here. This one is different. We'll be discussing here conceptual questions from electrostatics. Okay, not numericals. Like numericals can be included at some place, but mostly the questions will be conceptual. Okay, like the why, what, those kind of questions. Okay, conceptual discussion. Conceptual discussion on electrostatics. Right. So we'll be doing some questions that are theoretical and can come in 1 mark. Okay, like why this happened, why that happened. So question number one. Okay, why do the electric field? First, what do you need to do here? When I write the question, you just pause the video. Try to think why. Why? What is the answer? Okay, and then only you continue. Otherwise, there is no point. Not form closed loops. Why don't electric fields? Why do the electric field lines not form the closed loops? Okay, can pause the video. See, these are called electric field lines or lines of force. What are electric field lines, first of all? So, one question we will do different type of concepts. What is electric field line, first of all? Electric field lines are what? Electric field lines, for example, this is a positive charge Q. Okay, so if I leave it alone, okay, so what trajectory it will follow? What trajectory? Trajectory means path. It will follow. That is the direction of electric field. So that is a what? That is a electric field line. What trajectory would a what positive charge will follow? Okay, when left all alone, that is your electric field lines. Okay, so basically gives what? This basically gives me the direction of electric field. Direction of basically gives the direction of electric field. Okay, so first of all, so what are the properties? First of all, is for example, this is a positive charge. Electric field lines come out of positive charge. They go away from positive charge, right? But they end at what? They end at a negative charge. Okay? So we can say electric field lines what? They start at positive charge and end. There is always a starting point and ending point and negative charge. They never converge. Okay. Converge means what? Like never meet. Like never meet or intersect. Alright? They never meet or intersect. Why? Why don't they intersect? Because for example, this is the one electric field line, E1. This is another electric field line, E2. Why don't they intersect? Because see, what is the electric field? What is the field line concept again? For example, this is a point. What is the direction of electric field at this point? The tangent to this curve is the tangent to this curve is the direction of electric field. So this is the direction. So at one point there is always one direction of electric field. Okay. If I draw another curve intersecting this, so for at this point, this is an direction. For this ray, this is for one, this is two. For one, this is the direction of electric field. For two, this is the direction of electric field. So at one point, I'm getting two directions of electric field, which is not possible. Electric field can have only one direction at one point. Okay, that's why electric fields will never intersect. You have to write like this. Okay, they will never intersect. Alright. Why they will not form closed loops? Why electric fields are not like this? These are magnetic field lines. Magnetic field lines form closed loops. Why not electric field? Because electric field lines, the thing is, they will start from positive charge. Okay, they will always start from positive charge. They will end at negative charge. All right. Magnetic field lines, they make circular loops. Okay. All right. Yeah. Is that correct? Is that correct? All right. Did you get it? Okay. Next question. So from that question only we discuss so many points. Another point, for example, this is a conductor. Electric field lines will always be perpendicular to the normal to the surface of the conductor. They will always be normal to the surface of the conductor. Alright. Okay. Next question is, okay. Next question. Why are electric field lines perpendicular at a point on an equipotential surface of a conductor? Okay. Why are electric field lines perpendicular at a point on an equipotent surface of conductor? This is a conductor. Why the electric field lines are always perpendicular? I just told you in the previous slide that these are perpendicular. Okay, but what is the reason? Why? Why is it perpendicular? We should know that. Hey, so this is the one more question. Why is it perpendicular? See, why is it perpendicular? Because, for example, the electric field was not perpendicular. It was like this with a theta angle. So if electric field vector is making theta angle with this surface, then there will be two components of electric field along the surface. One is sine theta for a vertical component, another is e cos theta, that is horizontal component, because the component along with theta is e cos theta. So there will be two components, but there will be always a horizontal component. Understand it very well. Horizontal component. The horizontal component will always be there. Right. So what will this horizontal component do? So what will happen is like this is non-zero component. Okay, this is a non-zero component. So what will happen? You have the charges, like you have to move the charge against the direction of the component of the field. Okay, inside the conductor. So what will happen? For that, work would have to happen. If you are moving a charge against this, work would have to happen. Alright, but work done is what? Work done on an equipotential surface is zero. Why is that again? Why work done on an equipotential surface is zero? And what does that have to do here? See, work done, why work done is on an equipotential surface is zero? For example, this is an equipotential surface. Equipotential surface. Equipotential surface. What does it mean even? Means a surface where potential is same everywhere. This is V is equal to 2 volt. 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 So everywhere potential is same. What is the formula for work done? Work done W is equal to VA minus VB, change in potential difference by charge. What is the potential? For example, I am moving a charge from here to here. So what is the potential difference? 2 minus 2 by Q, that is 0. So work done on a equipotential surface is 0. because this is the same potential. Okay, so you don't have to do any work to move the charge. All right. So Warden is zero. If Warden is zero, okay, so we if Warden is zero, we cannot move. But Warden is zero here. That means how would you move the charge now? How will the charge move? Because there is already electric field on the horizontal component. So if there is an electric field, it will move the charge, right? See the beauty of it. This is a conductor. This is it's saying equipotential surface of a conductor. It's said in the question. It's said in the question. See, equipotential surface of conductor. That means your Warden is zero. That means don't have to do any work to move the charge. No work to move the charge. Okay, but there is a electric field component that is horizontal component E cos theta. If electric field is there, so charge will move, right? Charge will move, but there is no work done. You cannot do work on the charge. If you are not doing work on the charge, how will the charge move? So it is contradictory, isn't it? You cannot do work. How the charge will move? That's why this is not possible. That's why what electric field component is always perpendicular. All right, did you get it? Did you get it? Okay, yeah. That was the question. Okay, next question. Next question. Okay, next question is interesting. Number three. How does the electric flux due to a point charge? How does the electric field due to a point charge enclosed by a spherical Gaussian surface, get affected? Write the question. Okay, don't just sit and watch the video. When its radius is increased, how does the electric flux due to a point charge enclosed by a spherical Gaussian surface get affected when its radius is increased? You first think about it. 2 minutes. You have 2 minutes to think about it. How does read the question 3 times, even 5 times possible. See how many times I am reading the question. Okay, so read it again and again. What's the problem? How does the electric flux due to a point charge enclosed by a spherical Gaussian surface get affected when its radius is increased? Okay, how does the electric flux due to a point charge? Electric flux due to a point charge. Now the third time we will be starting to draw the diagram. Okay, how does the electric flux due to a point charge? There is a point charge enclosed by a spherical Gaussian surface. Spherical Gaussian surface. What is a Gaussian surface? It's a imaginary surface we are drawing for our own convenience to get the electric field and all. Okay, get affected when its radius is increased. For example, this is a surface. This is R. You are asked electric flux phi. How is it affected? Okay, if the radius is increased, not a, how much will be phi dash? If I increase, for example, if I increase the radius to 2r, so will the flux change? How will it change? Tell me in the comments. So, what will happen? What is the? It's a very easy question. What is the flux formula? Electric flux. Simple, basic definition of flux is Q enclosed by epsilon naught. Okay, Q enclosed by epsilon naught. That is the flux. Q enclosed by epsilon naught. All right. So this is your Gaussian surface radius r. What is the total charge enclosed? Enclosed in total charge q. If I increase the radius to 2r, now what is the charge? Tell me. Did it become 2 cube? The charge is there, na? How will the charge change? The charge is already there. It won't change. The charge q dash will also be q. We just increase the radius of the sphere. We didn't increase the charge. The charge is already there. We cannot increase it. So the charge is constant. So charge is always constant. Q enclosed is constant. Even if we increase the radius. So it's the same thing. So flux will remain same. So flux will remain unchanged. Is that clear? Flux will remain unchanged. Okay. With even if you change the radius, even if you do whatever to the surface, it will remain unchanged because the charge enclosed is constant inside the sphere. Okay. So this is another concept. Question number 4. Question number 4. Just wait a minute. Let me find a question. You must be thinking I slept or what. Just wait. Let me find good questions so that we can solve good questions. Okay, I know. Which orientation? Which orientation of an electric dipole of an electric dipole in a uniform electric field in a uniform electric field would correspond to would correspond to stable equilibrium correspond to stable equilibrium. Which orientation of an electric dipole in a uniform electric field would correspond to stable equilibrium? First of all, what is orientation? Which orientation? What orientation? I don't know what is orientation. If it is asking the question, what is I don't know. So how to guess? How to guess if you don't know what is orientation? Which orientation of electric dipole in a uniform electric field will correspond to stability? Electric dipole minus Q plus in a uniform electric field. What orientation would correspond to stable equilibrium? Orientation means what? What kind of movement, or what kind of movement, or what kind of like how it will move so that it will correspond to stable equilibrium, or what is the angle it is making with the electric field? Okay, what is the angle it is making with the electric field that will correspond to stable equilibrium? Simple. Okay, so orientation means what? Angle, kind of. What is this? Angle. So what is it? Tell me now. Hmm. See, when what is the thing? This is the electric dipole. Suppose, okay, electric dipole. This is P vector is from negative to positive. This is a E vector. So electric field wants what? What does it want? For example, like You are in a new classroom. Okay, so everyone is trying to make you acquainted with that class. Everyone is what make you trying to make you like them in the classroom. So electric field here is trying to make this dipole in the direction of electric field. Okay, so that it will orient in the direction of electric field. Okay, so that there will be no quarrel, there will be no other things. Okay, disagreement, so that everyone will remain same. So electric field will try to make it in the direction of electric field. All right. So after getting the direction of electric field, it will be called stable equilibrium. See, after you got adjusted to everyone, after you got with the equal terms with everyone, you will be called what? I'm stable. I'm now stable, settled. So that's what here also. If the dipole is now in the direction of electric field, that will be called a what? Stable equilibrium. That means dipole moment in the direction of electric field. Unstable will be what? Unstable equilibrium. That means dipole moment is anti-parallel to electric field. That means it's exactly opposite. Dipole moment is exactly opposite to electric field, then it will be unstable. Alright, did you get it? Yeah, this is the concept of stable equilibrium and unstable equilibrium. Okay. So your potential energy is minus P dot E. So for stable equilibrium, that means minus PE cos theta. For stable equilibrium, theta will be what? Parallel. That means 0 degree. So U is your what? Minus PE. For unstable equilibrium, theta is what? 180 degree. So cos 180 is minus 1. So minus PE minus 1. That is PE. This is a what? Potential energy. Alright. So if positive potential energy, then it's unstable. If negative potential energy, that is stable. Alright. This question is done. Okay. Is it clear? If it's not clear, let me know in the comments. Next question. Next question. There is a surface like this. This is plus 2q minus q. There is a charge plus 3q. This is a surface S. Okay. Hmm. So two charges plus 2 minus q are enclosed within the surface. Okay. So question is what is the electric flux? What is the electric flux due to the configuration through the surface S, through the surface S. Try first. 2 minutes. You can pause the video, and after that you can see it. Pause the video. Now I'm going to discuss. Now pause the video. Try first. Otherwise there is no point. Otherwise my videos will be worthless for you. If you don't solve yourself, it's worthless. It's pointless. Okay. So this is C. What is your Gauss law? Gauss law is flux is what? Q enclosed by epsilon naught. So tell me, what is the Q enclosed? This is the surface, right? What is the Q enclosed? Enclosed means the charges inside. Enclosed means inside charges only. What are the charges inside? Plus 2q minus q. Is it plus 3q? No. Plus 3q is outside the surface. So we'll only consider these two. Okay. So q enclosed will be plus 2q minus q by epsilon. That is q by epsilon. Over. Finished. Is it clear? Plus through q is outside the surface. Gauss law always talks about enclosed charge because this is your Gaussian surface or any no, this is not Gaussian. Like this is a surface, only a normal surface. So inside the surface, how much charge is there? Is it clear? Yeah, good. So these are the questions. Write some homework. Homework is question number 6. Show a plot. Show on a plot the nature of variation of the one electric field in potential V of a small dipole with the distance r. Of the distance r from the center of the dipole. Okay, we have to plot the nature of how electric field varies with r distance r and how potential varies with distance r. Okay. Another question, two questions. Does the charge given to a metallic sphere depend on whether it is hollow or solid? Okay. So these are two questions you have to solve. Okay. Okay then. That's it for today. We will discuss more conceptual questions like this, okay, in upcoming sessions. Thank you.